Okay, so yeah, we start now. This is the last part of the OP amplifier. So the another application is a relay. Relay, just now as well, I mentioned before, is being used to switch on a greater current by using a smaller current. As you can see here, the diagram, it consists of two diodes at there. So we have a D2, and then there is a D1, and also this is the earth point. So you know, right, the earth point, the voltage is 0. Okay, so means if I ask you a question, right, what type of output that you expect to come out from the OP amplifier, so it will allow the current to flow to the coil. Is it positive or negative? If our OP amplifier is negative, have a negative output, that means the current actually will flow from the earth point to the negative part. Okay, nothing is wrong with that. You can withdraw the current from the earth point, but it cannot happen at here because as you can see the D2 direction, how does the D2 direction point? The D2 direction is pointing down. So if your output is negative and you expect the current to flow out, it won't happen because it's being rectified by the diode. But then if your output is positive, then the current will flow down to the coil, and so I'll write the current will flow through the coil. So the coil will turn into electromagnet. But let's think further, discuss further. If you switch it off, so it means your coil will have a change in magnetic flux. So for those who never take IGCSE, change in magnetic flux means like you have a change in the magnetic field strength. So because your coil has turned into electromagnet, since there's a current flowing through the coil, and then suddenly you cut it off because you want to switch off your device. So it means you are changing from there's there's a magnetic field becoming no magnetic field. Okay, if there is a change in magnetic flux, it will induce EMF. So if it induces EMF means it will induces or produces current. Means it induces a current flow. Okay, so your D2 at here also have another function. Yeah? So the D2 is protecting the OP amplifier from the induced current. Okay, so probably the questions from some of you is why it have to protect the OP amplifier. You remember last 2 weeks when we learned about this basic discussion, we talked about there are two types of resistance in an OP amplifier. We can discuss it from the input side and from the output side. From the output side, the resistance have to be 0. But for the input side, the resistance have to be infinite. Okay. So if you don't have a diode protecting it at the output side, if your current, the induced current just now flow up, let's say the D2 doesn't exist, yeah, and then you have an induced current and the current flow up, it will cause the OP amplifier to be damaged. Because the output resistance is very low, and then suddenly there's a current that flow in. So if the current is, usually the current produced is relatively high, so it can cause your OP amplifier to be damaged. So your D2 also has another function actually. The other function is to protect the OP amplifier. The first function just now I told you is like to ensure the current flow from the OP amplifier downwards, right? Cannot be upward, right? Okay, this one is also to protect the OP amplifier. Then what is the function of the D1? Probably you are questioning like that. Well, you have to remember the induced current is actually in a alternating form. Alternating form means your current sometimes is heading upward, sometimes is heading downward. Yeah. Okay. So your D1 will answer the current, right? Flow in this direction. So whenever it want to go up, just remember the D2 will be blocking it. So your current will be flowing in this direction. And by time, right? You remember in AS level, when your current flow, there is a resistance, right? So the electrical energy will be used up. I mean, by the time the current will stop flowing, then you can switch off the relay safely already. Any questions that you want to ask until here? So B is equals to force over IL. If you're being asked for the definition of magnetic flux density, you can refer to the formula. So it's a force experience per unit length. Okay. The units for B is Tesla. So if he asks you to define 1 Tesla, then you can use the previous understanding, but then you just have to substitute all of the value by 1. So I mean, you can write something like when a wire carrying a current of 1 ampere, one Newton per meter of its length. Yeah. So for those who not take IGCSE, right, this one is about the Fleming's left hand. Yeah? Well, it can actually be left hand or right hand. There are two discussions, but now we are at the Fleming left hand rule. In short, right, Fleming left hand rule is changing electrical energy into kinetic energy. So which means you need to supply current to produce motion. Also, there's a law that you have to understand. If you have a moving charge which cuts through a magnetic field perpendicularly, then it will experience a magnetic force, which is perpendicular to the magnetic field and the direction of a moving charge. Okay, so probably it will be a bit confusing for some of you who are like new to physics. The simple case that here that you use daily is motor. So motor is something that can rotate. This includes the fan that you are using and the blender that you are using in your daily life. You supply electric current, right, into those devices, right? And you can see the blade is turning, isn't it? Okay, so you supply electrical energy, and inside the device, there is a magnet. Inside your device, there is a magnet. So your electrical energy has a moving charges, which is electrons. Your electrons are cutting through the magnetic field perpendicularly. That's why it produces a magnetic force, which then causes the blade to turn. Okay. When I say they need to cut through perpendicularly, so yeah, the students ever ask it, is it a must to be exactly 90 degree. No, actually, as long as you have a component which is perpendicular. I'll give you an example. So let's say this one is a magnetic field, as everyone know, right? Pointing from north to south. Yeah, I think you all of you know that already. It's supposed to be. Let's say you aim the charge moving in this direction. Are they perpendicular to each other? No. But then you have learned factors, right, in AS level. So your charge, the speed, you can split it into two components, right? The x component and the y component. And let's say I take that as a theta. It means the x component will be something like a cos theta, and the y component something as like a sine theta. Do you understand until here? Well, however, you still have one component which is perpendicular to the magnetic field, right? So in this case, you still will produce a magnetic force. You still will experience a force. Okay. But if the second case, if you make the moving charge like exactly parallel to the magnetic field, so in this case, there will be no magnetic force. Yeah. And probably you read either textbook like the national textbook or the IB textbook, right? They already derive a formula. So they like to give the students a formula where they write the F is equals to B times I times L times, I forgot, they write a sine or cos. Well, my suggestion is you don't need to memorize the formula in terms of sine and cos, because the matter of sine and cos is actually the understanding of which component that you have to take, and you have to take the perpendicular one. So those textbook that you are reading, right, with the term sine and cos, right, because when they derive the formula, they have an agreement in the textbook. Like probably the theta they are taking is to the vertical axis. So later if you read another textbook, right, if the derivation is to the horizontal axis, then the formula become different. So probably one is using sine, and then another one is using cos, and it will be confusing for you if you memorize the formulas. So just use the understanding that you have to take the perpendicular perpendicular component. Do you have questions until here?
No, sir.
No. Could you please take a photo of this first, because I'm recording it. So I will just explain it first like that. Oh, okay. I will clear the board. Okay. Okay. So now I have to go through the Fleming left hand first. Yeah. Probably like some of you have forgot. If you remember, then good. We use our left hand, your left hand. Okay. The first finger is the direction of the magnetic field. Your second finger is the direction of the current. So it means oppose the direction of electron. Yeah. I hope you still remember this. So if the electron is going right, the current is going left. The flow is another way around, right? In AS level, we ever discussed this. So actually, we use thumb also, but then actually you have to use your thumb and this is your first finger, right? This is the second finger. But practically, I found that the students have difficulties when they use this. So for your second finger, you just can keep it. So just focus on the palm. So we just use your thumb and your first finger. Your second finger directions is the same with the direction of the palm. So you can just keep it. Okay. So the thumb is representing the motion. The motion in here is the magnetic force. The magnetic force motion. Okay. We go example. So keep in mind that Fleming left hand is you should supply the current to get a motion. So if you meet equations where there is no current given, means that it's not Fleming left hand. Fleming left hand, you should give the current to get the motion. So if they give a motion and expect to have a current in return, that is Fleming right hand. Okay. Now, let's say you have a coil and the current is flowing upwards, cutting through a magnetic field like this. And then we're going to check or discuss where will the coil deflect. The coil will deflect to, you know, right? Magnetic field always go from the north to south. Right? You can draw first. Which of the finger representing the magnetic field? Your first finger, left hand. Don't use your right hand. So your first finger, you have to point it to the right of your screen first, following from the north to south. And then your second finger is the direction of the current, right? So we are using the palm. Make sure the palm is going up because you see the current flow up, right? So your first finger is pointing right, but then your palm is facing the ceiling, the top part of your room. So if you do it in the right way, your thumb is pointing into your computer screen now. Your thumb is pointing into the computer screen. Any of you confused? No, okay. So the coil deflects into the screen or into the paper. So you'll find the coil moving inwards. Okay. So let's say another case. Use an electron. If electron is flowing out of the screen, where will the current flow to? Into the screen. Use your Fleming left hand. The first finger is to the right also. And then your palm in this case have to be facing into your computer screen. Because it should oppose the electron flow. Where will your thumb be pointing? If you did it right, your thumb is pointing downwards. So it means the wire will deflect downwards, not outward. So I repeat it, this one is downward. So I ever meet a case where the students like have a difficulties in interpreting downward and outward. Okay, what is the law that we state just now, or the one that you photo as a? If you read it carefully, I write just now, when a moving charge cut through a magnetic field perpendicularly, the moving charge will experience a magnetic force in a direction which is perpendicular to the magnetic field and also to the direction of the moving charge, right? You understand 3D in mathematics? Your Z, your X, and your Y, they are all perpendicular to each other, isn't it? So I can tell you make a mistake if just now at questions number 2, right? You give me a comment of outward. If outward means out of your computer screen, then how can your motion and the direction of the charge are parallel to each other? What does the law state? The motion should be perpendicular to the magnetic field. So I mean, if you talk about these three things, right? Magnetic field, the motion of the charges, and the magnetic force, right? It should be perpendicular. So it means you should have the axis X, Y, and Z. Anyone have questions until here? Okay, you can write down first. The reason I don't give you revision for physics like chem is because I want to cover this magnetism version. Magnetism chapter and nuclear is quite challenging, so I need to cover one of this big chapter first, at least the magnetism verse, until I can give you a revision. Okay, next one is like practically if you want to measure the magnetic flux density, you should use what device? Uh, we have to use a device called by Hall probe. So Hall probe is consists of a plate, and you have to make sure the magnetic field cuts through this plate perpendicularly. You have to remember magnetic flux is a vector quantity. Magnetic field, electric field, they are vector quantity. So there are several versions of a Hall probe. Depends on the price also, right? If uh, the setup quite complicated, you have to connect it to a voltmeter. So later, there is a relation between the magnetic flux density that you are measuring and the reading of the voltmeter that you are reading. We will learn like their relationship also, like how to derive the formulas. And if you don't have this device in your science lab, right, that is fine. Because later we also will discuss how to have another setup in checking the magnetic flux density of a magnet. Okay. Now, if let's say you have this device and then you want to measure the magnetic field. So as I mentioned before, the magnetic field should cut through the plate perpendicularly, right? How can we make sure that is perpendicular? Well, at first, however, you have to try your best to make it perpendicularly also, like a common sense. Let's say the shape is of the magnet is U shape. Then somehow you know, right? Even though the magnetic field is invisible, but somehow you know it flows in this direction. So you try your best to set the plate perpendicular to the invisible lines. And also, right, do not take the reading immediately. So you have to like observe when you move the probe, right? When you place it at there, you have to observe the deflection of your voltmeter, and you have to really pay attention on the values because the value that you're gonna take is the maximum value. So you can say that it's perpendicular already if it gives you a maximum value already. Uh, In this experiment, if you repeat it for several times and you find the average, it will be a waste of time. The technique is not like that. So the technique is you need to turn the probe 180-degree. I mean, let's say just now you are holding the probe in this position and you place it at here in the middle and it give you a reading already. And in your report, you write like you take several readings and you find the average. That is not accepted. Taking several readings is a must. But then in your instruction, right? I mean, like in your steps, right? You have to mention you flip the probe. So you have to rotate it. Like let's say your handle is at the right. So your second experiment, your handle must be at the left. Now, you ever aware that your voltmeter has two deflections, right? Can be positive and can be negative, is that? So later, if you switch the position, it will be negative. If your first reading is positive, then your second reading will be negative. So when you want to take the average, right? In your report, you also have to mention you ignore the negative sign and you just take the magnitude to find the average. You need to mention it's being rotated 180-degree, and you have to ignore the negative sign and only focus on the magnitude as the average. Any questions until how to use the helper? No. Okay. So now we're going to discuss about the Hall effect. So actually, what happens inside the plate? Like, why we can measure the magnetic flux density? So I draw the plate separately. Where does the current flow? So actually, your Hall probe will have current flow also. So that is a current flow through your Hall plate or your Hall probe. So like your hull plate or your hull probe is using a battery also actually. And the B is the magnetic flux density, right? The one that you are checking. So please use your Fleming left hand. For this case, where will the current be deflected to? So your second finger or your palm in this case is facing downward and the B is facing inward. So if you did it right, your thumb is pointing to the right. So the current is the charges inside the current is going to the right part. Means later at the left side there will be a negative charge. Yeah, maybe some of you like confused. I thought you say current is the same direction with the positive charge. Yeah, I mentioned current direction and the positive charge direction is the same. But then what type of charges do you find inside the current flow? Do you find a positive charge? No, you don't. You find a negative charge. So your electrons will be gathered up or will gather up at the right hand side. Okay. Well, actually, there is no charge at the left hand side of the plate. But then since you make the negative intensity is getting higher and higher at the right hand side, it means at the left hand side, it will appear to be more and more positive. I hope you understand until here. Or you have any things that you want to clarify first? So if even you don't connect it to a voltmeter, let's say you buy a hall probe that not connected to a voltmeter, you can manually connect your voltmeter right to these different plates. Your voltmeter can like have the junction, right? So like one junction you put at the negative or the right side, another junction you put at the positive, and it will show you the deflection already later. It will show you a reading. So it acts. This I'm explaining how we have a voltage. So it builds up a voltage because the electrons is being gathered at one sideness. That's why you have a potential difference between two plates. So it means you have an electric field right now, right? How does electric field, uh, how should you draw the electric field in AS level? From positive to negative, right? What is electric field formula? You remember? F over Q. Remember? Volt over the separation. You remember this formula, right? Okay, I need it. Okay. So now I want to make the force as the subject. So the force is equals to volt times Q divided by the separation. The separation is between two plates. Uh, Back to the like the capacitance concept again. So yeah, I tell you that the negative charge will gather at the right hand side. But is it possible to keep on increasing the negative charge? You understand what I'm questioning you? Until one time, right? Until one time it will be like dense enough right here. Okay. So if you have reached that moment, it means you cannot keep the electrons anymore at the right hand side. And if someone asks you why, because there is a repulsive force between the electrons and the electrons that you're gonna put in. Do you understand until here?
Yes, sir.
Okay. If you have reached that case, it means you have an electric force, and the electric force is equal to the magnetic force. The electric force is the repulsive force between the electrons. So what is the magnetic force? The magnetic force is the Fleming left-hand rule. Just now you use Fleming left-hand rule, right? And from the Fleming left-hand rule, you understand that the electrons is being gathered at the right-hand side, right? So if you fail to force the electrons to go to the right-hand side, It means your magnetic force has been balanced, has been cancelled by the electric force. That's why you cannot do it anymore. Do you understand how I get this equation from? Times I times L, right? And on the other hand, you know the I is equals to Q over T, is it? So if you have a measurement in length divided by time, it will give you speed. And it will be confusing if I write down the term as V also. So I decide to write it as C. So you got a new formula now, B times Q times C. So just now you, on the other hand, you have like a magnetic force, right? Magnetic force you replace already with BQC. And then the electric force is V times Q over the D. You remember about the mean drift velocity? So the mean drift velocity in the AS level is given by I equals to uh, NAC, actually NAVE, but then the V is a speed, right? So I just write as a NACQ, and I made the Q as a subject, so it become I over NAC. You understand over here?
Yes, sir.
Okay, I move to the most right, the top corner. So about the area is the one that perpendicular to the current flow. So in the previous slide, how does the current flow? The current flow perpendicular to the top or the bottom area, right? And if you want to calculate that area, it will be the separations that we call as D, multiply with the thickness of your plate. That's why later the area I replace by D times D. Then I just substitute the Q on the right hand side one, and you can cancel out the stuff. So your final expressions to count the half voltage is given by B times I over NTQ. Okay, now, so just now I tell you, right, there is a relation between the B and the V. So this is it. So if you have this device at your science lab, so it means if you have the reading of the voltmeter, then you have the value of the V. About the value of the current flow, then you need an ammeter. If you want to know how much the current is flowing through your Hall probe, then you can just use an ammeter to measure that. Okay. For the thickness of the probe, you can measure it by using a meter rule. Usually it's several millimeter thickness. Uh, for the Q, what is the charge of the electrons? Of course, you know, right? 1.6 times 10 to the power of negative 19 coulomb, isn't it? What is N? N is the number of density per the electrons, right? Remember the AS level 1? So it depends on the materials. Usually you can browse like or when you buy the Hall probe, they have written at there like your Hall probe is being made up of what types of semiconductor. So later you can check at Google like the value of the N is how much. So yeah, there's another thing that you have to know. The plate is being made up of a semiconductor. Why? Because the N value is will be like a low, and the T also have to be, the T has to be thin, right? Yeah, the question is why you have to make it like that? Because if you make the thickness is thick and then the N value you make it like very high, it means the reading of the voltmeter will be very low, right? Then it will be very difficult for you to read your voltmeter itself. That's why in choosing the materials, you have to consider these two problems also. The value of N and the value of the T. So so far until here, you have any questions? No. Okay. If no questions, I will clear the board and continue and explaining again. Wait for it. I'm checking the maths questions. Okay, I'll clear the board. Just now I mentioned, right, if you don't have the device in the science lab, then what device you should use, right, to measure the half voltage. You can do this at home actually. You can just use a balancer, but then of course I suggest you to use an electronic balancer. So the idea is to have a balance here, and you check the weight of your magnet first. So you check the weight of your magnet, and then you like prepare a set of wire, and you connect it to battery. I think the battery should be like a quite a lot here. Yeah, of course, you know the wire cannot be like hanging in the air, right? Then you have to put some block or what, right? You tape the wire onto the block, right? And you can buy ammeter, right? Can I mean you still can measure the own current flowing on your wire, isn't it? Okay. So when the current cut through the magnetic field, it means it will experience a force, right? But then there are two options for the force. The force can be going upward, or the force can be going downward, right? I mean, we need to know the north and the south poles also, but that is not a problem, because however you will have the change in the reading, right, of the balance, right, like how many grams, right? So you will be able to change it to how many Newton. Then the question is, um, if there is no magnetic force, will there be a change in the reading of your balance? Then the answer is no, right? So it means you have understood that the change of the weight, this one is equals to the magnetic force. And you can equate it with the formula B times I times L. So you will be able to calculate the B. Can calculate the B. So the next question is which length should be used, right? You understand until here?
Yes.
Okay, about the length that you have to use is only the length that you place inside the magnet. Let me draw, yeah. So you just use the wire that cut through the magnet itself, so only like that thin, maybe couple several centimeter or anything. But then the limitation is, um, well, there is a student, an IB student, so she ever carry out an experiment creating B and shape. So if you use this setup, then not all of the shape you can check the B. I mean, if you have a like a button magnet, that is quite challenging already. You have to figure out how to make two button magnet like that, right? And the wire. If you have a Hall probe, yeah, that is very easy to be used, right? I mean, you still can do the experiments. It's just like quite troublesome. Only the setup have to be a little bit more complicated. You have questions that you can ask until here?
No, sir.
No. Okay. Could you please take a photo of this first? I can give you one more example. We are learning like 2 chapters at this one. This one is quite long. For magnets, there are 3 chapters which are related to each other. Oh, sorry. I think around 4. Yeah, 4 chapters. Okay, the next one is, it's just a word problems actually. The red one is the magnetic field. So I just want to ask you, in your opinion, if I have this kind of setup, right? In which part of the coil will you find a magnetic force? AB, BC, or CD, or all of them, or how? You cannot find it in BC, because if in BC your current and the magnetic field is perpendicular. Sorry, your current and the magnetic field is parallel to each other. Right. So means you only sorry. Just now you can, hello, you can still listen to my explanation until which part? Yeah? You can listen to the explanations until which part?
Until BC don't have the one answer.
Okay, okay, thank you. So if you use your flaming left hand, the current is flowing in this side and flowing out in this side. You will be able to tell that the force is acting downward in this side and the force is acting upward on the other side. I just found out that there are some students that don't have a self-confidence in solving this. So when they want to count the magnetic force, right? I don't know, they know the formula, but then they are not sure about like what to use. So if you talk about the length, when you say the wire that experience the force is AB and CD, is it? So it means the length that you are talking is the length of AB or the length of CD. The thing is clear until here. But then you remember the couple? The turning effect of force, we have one discussion about a couple in AS level. So both of the forces at here could be called as a couple, right? Because there is a resultant moment, but there is no resultant force. What is the formula for the turning effect of force? You will be taking one of the force and you multiply with the separations, right, between two forces, right? So what is the separation between two forces that you have to use at here? Which length is it? I mean, do you use the length of AB? No, you don't use the length of AB and also not the length of CD, but you have to use the length of uh, BC. Any question until here?
No, sir.
No, okay.